Hello, and welcome to the introductory course on computer architecture. My name is David Black-Schaffer, and I'll be the lecturer for this class. Right now we're going to start out going through what are the contents of this course and what we're going to cover. We're going to start out and talk about the course, what is computer architecture and what do you have in there. And we're going to focus on something in particular, why should you care about this? So why are you taking a course in computer architecture? What should you expect to get out of it? To do this, we're going to look at a modern example, and this is the big. LITTLE processor. We're going to look at the example of why it's interesting, and then we're going to go into some of the details about how computer architecture relates to this example. By the end of this, you should have a feeling for what sort of things you're going to learn in this class. We're also going to talk about the course logistics, in particular what a flipped classroom course is and why we're doing that in this class, and how the grading and assignments in this course work. So let's get started talking about the course. So this is an introductory course in computer architecture. We assume you don't have any background experience in computer architecture, and it's not for the IT and DV students. They take the version of this course that's offered in the spring. The requirements for this course are just basic programming experience. So I don't really care what language it's in, C or Java are just fine, but you need to have some imperative programming language experience. So you need to know about for loops and if loops and function calls. This is the same course taught for both the distance and the local students. It means it's the same material, same assignments, everything's the same. And it's 7.5 points for the distance students. That means they're expected to put in 200 hours, and 5 points for the local students, which means they're expected to put in 133 hours. We estimate you'll need about 108 hours for this course. So this course is going to take a fair amount of your time, but it should be well under what you're expected to do for the number of units you get it. The local students are going to have in-class practice exercises. That is, when they come to the class, they're going to practice the exercises there in the class. The distance students, since they don't show up to class, are going to work on these practice exercises at home with partners, either remotely or in person. So what are we going to cover in this class? We're going to start out with how a computer is built. We're going to cover information on how you build logic, how you take the logic, put it together in circuits, and from that you build a data path, and the data path is where the data moves through the processor and does interesting stuff. We're also going to talk about how a computer is controlled. And this focuses on the microarchitecture. So the stuff going on inside the computer that controls what's happening. And the microarchitecture is controlled by instructions, and we write instructions using assembly language or an instruction set architecture. So we're going to cover those parts of how you control a computer. Then we're going to talk about performance. Performance is, of course, why we have computers in the first place. And we're going to talk about some basic stuff for how you do performance, pipelining and hazards, but then we're going to go into some more advanced issues of performance, branch prediction, caches to speed up memory, and parallelism to get more done at once. So throughout this course, we're going to use the MIPS processor as an example and talk about logic design, processor design, I/O, input, output, and memory, caches, virtual memory, and parallelism. Cover all these topics in this course. So you should probably be asking some questions at this point. The first one is, why should you care about this stuff? You're not going to go off and design computers. Very few people do design computers in this world. Another question is, why are we using MIPS? Most of you probably haven't heard of MIPS and certainly don't own a MIPS computer, so why are we learning about that? Well, the answer to the first question is, why are you learning this if you're not designing computers, is because architecture is essential for performance. If you want to write a program and get good performance, you need to understand these parts of the processor so you know why your program is or isn't fast. Why are we using MIPS? Well, that's a simple practical matter. MIPS is simple. It's easy to understand and it's good for teaching. The standard processors, x86 from Intel or AMD, are much more complicated and they're a lot harder to teach. Now, one question a bunch of people have had is, what does MIPS mean? What does it stand for? Well, MIPS stands for Microprocessor Without Interlocking Pipeline Stages. And this was a processor that was designed by the author of the textbook, John Hennessy, and made him quite wealthy. And for a long time, MIPS processors were the main high-performance processors in the world, and these days they're just used in printers. So what are the learning objectives for this course? Well, first off, we want you to understand the functionality and operation of the basic parts of a computer. So this includes the processor, the memory, and the input-output. And so you'll understand how those work and how you program them. You're going to also be able to reason about performance. So by the end of this class, we'll be able to give you examples saying, if you have this type of cache or this sort of branch predictor, tell me how much the processor is going to speed up or slow down, and you'll be able to analyze that. You're going to understand the hardware-software interface, and this is sort of the coolest part of all this. It's how does the software that we write actually connect to the hardware? What are the instructions? How do those instructions work? And finally, you'll be able to write programs in assembly language. And now, assembly language isn't all that exciting by itself, but it's a great way to get at this hardware-software interface and a great way to understand the functionality and operation. So assembly language is not a means and an end in itself, it's a means to understand the rest of the stuff.